Hello students. Our next example is which is the case of a block and string here in which we are considering the gravitational force also. Example. So here there is a m mass whirling at a velocity v. M is the mass and r is the length of the string and there is gravitational field downwards. So mass m is whirled at instantaneous speed v at the end of a string of length r. The motion is in a vertical plane. So we are considering a vertical plane. So there is influence of this gravitational force also. So the motion is in a vertical plane in the gravitational field of the earth. Okay. Now the forces on M are, there will be two forces. One is the weight mg downward and the string force T towards the center. These are the two forces acting on the mass M. Okay, the string makes an instantaneous angle theta with the horizontal. Theta is the angle made by the string with the horizontal. Now we have to find out what is the T, the string force T, and also the tangential acceleration at any instant. These two are the physical quantities which we have to find out. Okay. So here we know this is the direction of T towards the center, the tension or the string force towards the center. Weight of the body is that it's towards the downward direction along with G, and these are the unit vectors direction of R and theta. Okay. So in this case, here we are resolving the weight W into two components, W cos theta and W sin theta. So W cos theta is the tangential component of weight and this is the perpendicular component. W sin theta is along the direction of T. So in the radial equation of motion, along with T, there will be a component of W also. Since both are in an opposite direction towards R, there will be negative sign for both the terms. So the radial force is minus T minus W sin theta. So the radial equation will be minus, we have taken both minus outside, minus T plus W sin theta is equal to MAR. AR is the radial acceleration which we have dealt in the last video. So AR is equal to R double dot minus R theta dot square. This is the equation number 1. This is the radial equation of motion. Okay. Similarly, the tangential force. This is the tangential force acting on the mass m, which is opposite to the direction of the unit vector theta. Okay. So there will be a minus sign for the tangential force. So minus W cos theta is the tangential force. So our tangential equation of motion will be minus W cos theta is equal to m a theta. A theta is the angular acceleration term. A theta is equal to r theta double dot plus 2 r dot theta dot. This is the equation number 2. These are the two equations of motion along the radial and the angular directions. Okay, now we have to find out, we have to solve these two equations. Now we know that r is equal to a constant, which is the length of the string. So we have found out AR is equal to minus r theta dot square. We know theta dot is V by R. On substituting, we get AR is equal to minus V square by R. And when we substitute this in equation number 1, we get T is equal to mv square by R minus W sin theta. Okay, so there is an additional term minus W sin theta along with this term which we have dealt in the earlier example. So there is a minus term. So there is a decrease in the value from this term. Okay, when we take mv square by R outside, that is 1 minus gr sin theta by v square. So what are the conditions in which this the mass can move in a circular path? We have to define the condition for that too. Okay. We know that the string force can only push it towards the center. It can only pull but it cannot push out towards the outside. So T cannot be negative. Okay. This requires that if T cannot be negative means this term should be greater than this term, right? So mv square by r must be greater than or equal to w sine theta. So the maximum value of w sine theta occurs when the mass is vertically up, that is when sine theta is equal to sine 90, which is 1, which is the maximum value of sine theta. In that case, mv square by r is greater than w. This should be the condition to be satisfied. If this condition is not satisfied, the mass does not follow a circular path. It starts to fall and r double dot is no longer 0. Okay, that means r is no longer a constant. It starts falling and there is a relation equation in AR where r dot is no longer 0. So this is the condition to be satisfied in order to maintain that circular motion. This should be the condition. Now the second part is to be solved as the tangential acceleration, which is given by equation number 2. We know that r dot is 0. Therefore a theta is equal to r theta double dot. So from that equation you get a theta is equal to the tangential acceleration is minus w cos theta by m, or since w is equal to mg, when m get cancelled it is equal to minus g cos theta. Okay, so a theta is a varying quantity along with theta. Okay, so the whirling block has a tangential acceleration that varies between plus g and minus g cos theta from 0 to plus or minus 1. Okay, it varies from plus g to minus g no matter what is the value of v. Now on the downswing the tangential speed increases and on the upswing it decreases. Now if we want to swing the mass with a constant velocity, we would need to make a theta 0. So we want to make it a constant velocity. We want to make a theta is equal to 0 by giving t a tangential component w cos theta. By making a theta 0, we can make the swing with a constant velocity. This is the second example. So in the first example, we have assumed the gravity to be 0 and we consider in the second example in the gravitational field what is the variation in the movement of the string.